Welcome to this tutorial. Today we'll dive into Bayesian regression using NumPyro. We'll walk through a simple example adapted from statistical rethinking and explore key concepts step by step. Here's what we'll cover in this tutorial: writing a simple model using sample NumPyro primitive, running inference using MCMC, specifically the no-U-turn sampler to obtain a posterior distribution over our regression parameters, exploring inference utilities like predictive and log likelihood, understanding how to use effect handlers in NumPyro to generate execution traces, condition on sample statements, and seed models with RNG seeds, using these tools to implement utilities for MCMC, such as computing model log likelihood and generating posterior predictive distributions. First of all, we install NumPyro using pip. Here I am using Google Colab. Needless to say that you can use whatever coding environment you are comfortable with. I am also using a couple of Python libraries besides the NumPyro itself, like Matplotlib, JAX, Pandas, and Seaborn. For this example, we will use the waffle divorce dataset from Chapter 5, Statistical Rethinking. The dataset contains divorce rates in each of the 50 states in the USA, along with predictors such as population, median age of marriage, whether it is a southern state, and, curiously, number of waffle houses. Let us plot the pairwise relationship amongst the main variables in the dataset using seaborn.pairplot. From the plots, we can clearly observe that there is a relationship between divorce rates and marriage rates in a state as might be expected, and also between divorce rates and median age of marriage. There is also a weak relationship between number of waffle houses and divorce rates, which is not obvious from the plot, but will be clearer if we regress divorce against Waffle House and plot the results. This is an example of a spurious association. We do not expect the number of waffle houses in a state to affect the divorce rate, but it is likely correlated with other factors that have an effect on the divorce rate. We will not delve into this spurious association, but if you are interested, you can read chapters 5 and 6 of Statistical Rethinking book, which explores the problem of causal association in the presence of multiple predictors. For simplicity, we will primarily focus on marriage rate and the median age of marriage as our predictors for divorce rate throughout the remaining tutorial. Now we write a regression model in NumPyro to predict the divorce rate as a linear function of marriage rate and median age of marriage in each of the states. First, note that our predictor variables have somewhat different scales. It is a good practice to standardize our predictors and response variables to mean 0 and standard deviation 1, which should result in faster inference. In NumPyro, model code is any Python callable which can optionally accept additional arguments and keywords. For HMC, which we will be using for this tutorial, these arguments and keywords remain static during inference, but we can reuse the same model to generate predictions on new data. We model divorce rate based on marriage rate using the same code, focusing only on these two variables. Using the no-U-turn sampler for inference, we define a potential energy function representing the negative log joint density of the model. No-U-turn sampler operates in unconstrained space, requiring transformations for bounded variables, which is handled automatically by NumPyro's MCMC inference class. This class includes methods like run for sampling, print a summary for diagnostics, and get samples to retrieve posterior samples. To look at our regression fit, we plot the regression line using our posterior estimates for the regression parameters, along with the 90% credibility interval. Note that the HPD function in NumPyro's diagnostics module can be used to compute CI. Note that the collected samples from the posterior are all along the leading axis. We can see from the plot that the CI broadens towards the tails where the data is relatively sparse, as can be expected. Now we check that we have set sensible priors by sampling from the prior predictive distribution. NumPyro provides a handy predictive utility for this purpose. Note that for predictive to work as expected, the response variable of the models, in this case divorced, must be set to none. In this code, this is done implicitly by not passing a value for divorce to the model in the call to prior predictive, which due to the model definition sets divorce equal to none. To see how our predictive distribution looks with respect to the observed divorce rates, we look at the posterior predictive distribution. To get samples from the posterior predictive distribution, we need to run the model by substituting the latent parameters with samples from the posterior. Note that by default, we generate a single prediction for each sample from the joint posterior distribution, but this can be controlled using the numSamples argument. To remove the magic behind predictive, here we see how we can combine effect handlers with the vmap-jax primitive to implement our own simplified predictive utility function that can do vectorized predictions. It should be clear now that the predict function simply runs the model by substituting the latent parameters with samples from the posterior generated by the MENCMC function to generate predictions. Note the use of Jax's auto vectorization transform called vmap to vectorize predictions. Also note that if we didn't use vmap, we would have to use a native for loop for each sample, which is much slower. Each draw from the posterior can be used to get predictions over all the 50 states. When we vectorize this over all the samples from the posterior using vmap, we will get a predictions1 array of shape numSamples 50th. We can then compute the mean and 90% CI of these samples to plot the posterior predictive distribution. We note that our mean predictions match those obtained from the predictive utility class. We have used the same plot regression function as earlier. We notice that our CI for the predictive distribution is much broader as compared to the last plot due to the additional noise introduced by the sigma parameter. Most data points lie well within the 90% CI, which indicates a good fit. Please hit the like button. Subscribe to the channel. If this channel is a machine, your presence is the fuel. Without your support, these videos would not be published.